Hello and welcome to the KubeCon Japan 2025. In today's session, we will reimagine the cloud-native networks and explain the critical role DRA has in this transformation. I'm Lionel Jouin. I'm a software engineer at Ericsson Software Technology. I'm a CNI maintainer, contributor to the SIG network, to the Kubernetes network programming working group, and to the working group device management.
Okay, I'm Sunyanan Choochotkaew, or Pang, as you may know. I'm staff research scientist at IBM Research. And today, we're going to talk what Lionel has already mentioned. But before that, I would like to start about CNI and the current limitations of the current CNI. How many of you know about CNI in this room, I think? Oh, okay, everyone know about the CNI, I'm not sure, not everyone. So let me say a little bit about that. CNI is a CNCF project that actually I copied their definitions from the CNI repositories. But yeah, is this a CNCF project that have libraries, specifications, everything to write a plugin to configure the network interface for the Linux containers. To set up the networks of containers, admin or users have to define or choose the network configurations, whatever they want to have is in the pod or in the containers. And what's happening here is that that configuration is passed to the container runtimes, and the CNI binary executions just make it happen on the containers and give it to the pod. Okay, and this is straightforward nowadays to have these configs of the container networks. As long as user or admin know everything that which interface that they want, or how they want to configure the IP address of the container network, so everything works fine. However, whenever user don't know that, I mean, for example, in the heterogeneous cluster, you don't know which node your pods are going to be scheduled. It could have a different host network, could have a different host name. At the same time, you may want to have some advanced technologies like Rocky TDI. You want CPU and NIC in the same numbers to have the efficient communications. In that case, our user may not know about that, and also our user may just want whatever network interface that's available right now is not occupied by the other pod. They want the full bandwidth or something like that. It's something that users don't know in advance and cannot create the config in advance. In that case, just only the CNI framework right now may not serve that purpose. So that's here we come to the current talks. Reimagine Kubernetes network with DRA, which is only the CNI. We can maintain networks stuff is our admin task. That's main configurations. User choose it, and CNI is a tool to configure the networks. But with the DRA, now we have a partner, we have a friend. So instead of that, you can think that actually network card is just another device that is actually user device. And at the same time, CNI tools, you can think these are the tools that prepare the device for your pod or for your container. So the key concept of what we're thinking is that first, we're trying to adopt we're going to adopt the DRA frameworks for the network cards. So with just the point that we adopt, it means we extend the capabilities of the fine-grained selections of the device. We can do specific which NIC and which kind of the attribute that we want for the container. At the same time, we can do the topology-aware selections as well. The second step of the concept is that we don't want to throw away everything that the CNI plugins create. We want to use the CNI plugin, the existing one. So we have to implement the bridge between the DRA and the CNI. And the third one is that what is missing on the current DRA, the foreign network context. So before I continue, let me touch a little bit about DRA, but we have a lot of expert DRA in here. Please let me know if I tell something wrong. The device management before the DRA, in my understanding, is that, okay, we have scheduler connected to kubelet, and kubelet have some device plugin that have our information about the device. It's connected together with the kubelet, and the kubelet tell the scheduler availability of the device. And scheduler just check the availability of the device on each node. And when they see that, oh, this node has the device in there with availability number that they want, they just schedule the node and take the rest part for the kubelet doing allocating the device and stuff. However, when it comes to the DRA, it's like this. I mean, the request that come to schedule is not that simple, like I want one of the GPU or something like that. It will be like blah, 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 and blah, 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 and this can like context like multiple devices at the same time. So what we have here is that we have the DRA come up with the kubelet, and it say, yeah, here's the list of the device, here's the attributes and everything. So you reserve whatever you need, and then I will just follow your lead because you know everything. This is what I understand about the DRA machine. Okay, and this is how it's actually work with the implementations of the YAM5 stuff. We have a kubelet with the DRA who know about the device. It's provisioned to the resource like, and it's have a list of the device attribute and everything that I mentioned. At the same time, we have a user who have high demands of the configurations of the device. User make a resource claim what the device they want to claim, and then scheduler who know everything will make an allocations, do a reservations, and set the state back to the kubelet to make an allocations based on that one. This is how it's working generally, in my understanding again. Okay, so at the point, as I told, at the point that we adopt the DRA, what we can do with the networks. In this example, it shows a very simple topology look like that we have some PCI switch and we connect some our GPUs and our NICs. And then with this one, we can have a file grants to like specify the vendor of the NICs that we want. And at the same time, we can try to do topology-aware selections based on some attribute matching constraint. Okay. And then Lionel will continue on the implementation.
Right. To reimagine the cloud-native networks, why not trying to merge the two concepts that Peng mentioned, CNI and DRA? So we could have a CNI-DRA-Driver, and this DRA driver would just act as a container runtime plugin. So it will be just an extension using, for example, NRI, Node Resource Interface. So the container runtime will no longer have to call CNI by itself, but instead, the DRA driver will do it, or at least for now, for the secondary network interfaces. So this is not possible currently in container runtimes. So this driver would provide a unified and declarative approach. Unified because we would avoid the split between the device plugin and the network configuration part. So the device plugin could be, for example, the SRV device plugin, and the configuration part could be a CNI that will utilize Multus to create this secondary network interface. And it will be declarative because it will be fully integrated with Kubernetes. So we would no longer use any annotation or CNI in a JSON format in a CRD. It will be fully integrated with Kubernetes. So the first thing that this DRA driver would do is to publish the network resources available in the cluster. So it will publish the network interfaces with their capacities and their attributes. And then the user would just have to configure the pods and the resource claims that would request this network interfaces and provide the configuration for them. So Kubernetes will schedule the pod based on this requirement and will put the pods on the node where these resources are available. And the third part is from the driver. So the driver will configure, based on the resource claim, configure the pods and add this network interfaces, a bit like what Multus is doing. And also, it would set the status of this newly created devices in the resource claim status. So to achieve this goal, for achieve this goal for networking in DRA, with, for example, the CNI-DRA driver, two enhancements have been conducted. So the first one is about unifying the network framework. So gathering all the generic and common pieces and adding them to DRA. So for example, the status of the network devices configured with DRA will probably have an IP addresses or multiple IP addresses. So that can be reused for network services, for example. And the second enhancement is about sharing the network resources to provide cutting-edge features and consume, for example, the capacity of the resources in an efficient way. So, for example, we could consume the network bandwidth of a network interface and have it guaranteed for the pod. So, as mentioned, the first enhancement is about unifying the network framework. So the device status has been added to the resource claim status, so we can now report the actual device information, like the readiness or the conditions, as well as the IP addresses that could be reused, for example, for an endpoint slice controller to provide services over secondary networks. The endpoint slice controller would no longer provide select the IP addresses from the pod status pod IPs, but instead select the IPs from the resource claim status that would be attached to the pods. And the second benefit would be about the condition and readiness. So we could know, for example, if the network interface fails to be configured on the pod creation, or if there's an unexpected issue during runtime of the pod, then we could know the reason why this fails. So these use cases have been enabled by the KEP 4817, which has been released in Kubernetes 1.32 and is now in beta. So a new field has been added in resource claim status to provide the information about the allocated devices. So the new field is resource claim status devices. It's a list where each entry will match an allocated device in that resource claim, and each device will be recognized by the set of device name, pool, driver, and the share UID that Bank will present right after. And it will also have some arbitrary data, so it's not only for networking, it's also for any type of devices. So there's also a networking field that contains the IP addresses, the MAC address, and the interface name. So the DRA driver will have the responsibility to set the status for these allocated devices, and it can be set during the pod runtime, but during the pod configuration, but also during the pod runtime. So if the network encounter some connectivity issue, then this status can be set.
The second use case that we have is our guarantee shared network bandwidth. As you may already know, with the Kubernetes, you can set the limit of the bandwidth as well. We have the annotations, and it's we call bandwidth our CNI to set the TC for you. However, it has no guarantee. I mean, you can set annotations of 2 pod for 10 gigabit per second, 2 times, and it's scheduled to the same pod and get the same rate limit. So this has come to the second use case here that we want to guarantee that if you request a bandwidth for 10 gigabit per second, no one will take the same capacity from your device. So it's come to this use case. The example here we show let's say we have 2 kind of requests. One is saying they want the 10 gigabit per second of the networks, while we have another template of the request saying that, okay, we want just only 5 gigabit per second, but we have 3. And then at the same time, we have 2 worker nodes look alike that have ones of the 10 gigabit per second high-speed networks. As you can see here, what we want to do is that if they claim a 1 to 10, we give them 1. While the second one, they want 5, or for each round, we can schedule just only 2 of them on the worker 2, while another one have to be pending. So what you see here is there's 2 things happen that doesn't happen right now in the current DRA. One thing is that our synchronous individual requests can be shared in the same device on the worker B. The claim for 5 gigabits per second is allocated to the same node independently. And the second thing is, as I say, the main use case of this one, all can get the guarantee, the capacity that they want. So here comes the KEP that we have just pushing the PR from January as 5075 consumable capacity. We add 2 things to the DRA drivers resource slides that to do what I showed in the previous slide. One thing is the flag to say that we are allowed this device to be allocated multiple times by the multiple requests. Because, right now, we are not allowed that. And the second thing is that we define how we would like to have the capacity to be consumed or to be guaranteed. So this is two fields that we add to the resource slice. At the same time, we add also the field at the user side as well. When user make a request, how much they want to use, or the device that they want to allocate, this is the one that are allowed to share with the orders freely or not. So that is the part that we have to add. And in the status as well, after we make allocations, there is two fields add. One is saying how many is our capacity or how much capacity that allocated to this sharing, and also if it's shared with the order request. So what is how to differentiate it from the other request? This is a share ID that Lionel mentioned previously in the status. So this is what we propose a change in this cap.
So now let's have a demo about this. So we will run a demo with a modified version of Kubernetes that contains this consumable capacity because it's not yet released. So what we will do first is check the environment. So we will have 3 nodes, and 2 of them, we will call them KindWalker 1 and KindWalker 2, will have this ENP0 S10 interface that will not be included in the KindWalker 3. And we will create one pod first that will claim 10 gig of this interface by creating a MacVLAN interface based on it. And we'll create 3 other pods that will request 5 gig each of them in the same way, requesting a MacVLAN interface based on this ENP0 S10 interface. Then we will verify what has been allocated and what has been acquired by the pods. So let's have the demo now. So the first thing I would like to show you is the pods that are running in the cluster. So I hope it's big enough, but we have the CNI-DRA-Driver that is running in the cluster, and we have just a normal cluster for now. We will verify the nodes. So I will show you the nodes. We have the control plane that we will ignore, but we have the 3 other worker nodes. And we will check the interfaces in each of them. So in KindWalker 1, we have this ENP0 S10. In KindWalker 2, we have the same. And in KindWalker 3, we also have it. So we now verify the resource slices that will reflect the status of this network interfaces in an object called resource slice. So we have 1 resource slice per node. Oops. So let's check what is inside this resource slices. So we have in the resource slice for the KindWalker 1, we have ETH0 that is reflected and ENP0 S10 that is reflected with capacity of 10 gig, bandwidth capacity of 10 gig. Let's check the KindWalker 2. It's also the same, and KindWalker 3 doesn't have this ENP0 S10 interface. It has only the ETH0 interface. So what I will do now is that I will deploy the pod A that you can see in this picture. So let's check what is inside this YAML file. So in this YAML file, can we see? Yeah, we can. So we have the resource claim first that is requesting an interface with the name ENP0S10. That we will claim 10 gig of this interface via the capacity request. And we have the CNI config that will configure a MacVLAN interface based on this ENP0S10 interface. And we will also assign some IP addresses, so we can also demo the status. Now let's deploy the deployment B. So we'll deploy 3 pods. So in this deployment B, we are requesting 5 gigs in the capacity request, and it's the same CNI config, and we are requesting on the same ENP0S10 interface. So it's a deployment that is pointing to this resource claim template, and 1 resource claim will be created per pod. There will be 3 pods in this deployment. So what we can do now is to check the pods. So if we check the pod, maybe I can put that on the top. So if we check the pods, then we can see that demo A is running on kind worker 1. Demo B is, 2 of them are running on kind worker 2. They have been scheduled there, and they are utilizing the full capacity of bandwidth for ENP0S10. Demo A is using the full capacity for the same interface, but on the first worker node. And since there is no more capacity available in this cluster, then the last demo B pod is not being scheduled, so it's in the pending state. So if we check the resource claim, we can find the reason why this pod is not being scheduled. So it's still in the resource claim that this pod is pointing at is in the pending state, and the others have been allocated and reserved. Now let's check the resource claim for the pod A. So in this resource claim, we have in the result a consumed capacity of 10 gigs as requested. We have this share UID because we are using this consumable capacity and we are creating a virtual device here. And we have the device status that contains several information. The first information contained is the CNI result in the opaque data, but we can ignore this for now. And we have the network data that contains the MAC address, the IP address, and the interface name that has been configured in the pod. So if we check in the pod demo A, then we can see that the network interface net1 is matching the result of or the status of the resource claim. So it has the same IP address 10.10.1.2 and the same MAC address 92D17F. So as we could see in this demo, a CNI-DRA-Driver could work, but there are still remaining questions like how to integrate with all the existing CNI. The CNI ecosystem is quite large and is covering a lot of different use cases. We could imagine multiple different approaches to solve this problem. One could be one DRA driver per CNI plugin, but that would cause some problem, for example, because there would be no communication between the different DRA driver. So for example, if we have a VLAN DRA driver and a MAC VLAN DRA driver, then they would expose the same resources. They would expose this ETH0 and this ENP0S10 interface that we saw in the demo, and then the capacity would not really make sense. We could not consume the capacity in an efficient way, or it would simply not work. The second approach is the one that is currently being used in this demo, would just be to have a generic DRA driver that would expose as much resources as possible with all the attributes and capacities. But still there is some issue about it because some CNIs are using some specific features, like over the networks, they are using different data plane like OVS, VPP, and others, which makes things incredibly difficult to handle at the end. And the third one, or the third approach would be to enhance CNI to provide capability for the CNI to expose and publish the resources by themselves. But this would require the CNI to implement this kind of features and then would take quite some time. Another challenge around this work would be about the current de facto standard in Kubernetes to attach secondary network interfaces. So we have Multus, that is an absolutely great and simple approach, but it's not native in Kubernetes. As I said, it uses the annotation, for example, it uses CRDs and JSON format in these CRDs. And the use of DRA would provide all this capability that we saw in the demo, but and some cutting-edge features, but would be a bit more difficult on the user perspective. And the migration story would also have to be taken into consideration to switch between Multus towards a CNI-DRA driver, for example. So to conclude on this, we can say that there is great progress towards supporting networking in DRA, or using DRA. But for example, the resource claim status or the consumable capacity are enabling it, and there is a lot of different caps that are enabling networking. So for example, the prioritized alternative in device request or the donor API capabilities. And these changes are also an amazing step for the multi-network initiative, because this initiative has started back in 2022 and is still currently active to bring native support of multi-network in Kubernetes. So having a way to attach networks in a native way in Kubernetes is a great first step towards this multi-network initiative. And the last question here would be, do we need a CNI 2.0? So the CNI API could be aligned with what Kubernetes provide in the latest changes or in the latest version. So, and the latest changes that it proposed, like the features like DRA, for example, this is a question that remains. So if you are interested in being involved in this work and around all these communities, I would highly recommend there's 4 different communities. So the first one is CNI, Container Network Interface. The second one would be the Working Group Device Management, where we are talking mostly about DRA. We have the multi-network community that we are also mostly talking about DRA now on the networking side. And we have also the Kubernetes Network Plumbing Group, where we are talking about Multus and the future of it. So I would like to thank you for your attention, and if you have any question, please feel free. I guess there's some microphone around, or you can talk to us right after. Thank you.
Thanks. This was a really enlightening talk. Looking between your kind of architectural options of how to pursue DRA networking in relation to CNI, it seems like number 3 is architectural perfection. It's the desired end state. But as soon as you start talking about a 2.0 release of a specification that's used across 30 organizations, even beyond just the Linux Foundation, start to wonder if my grandchildren will be able to use it. So is there a path where we can say make the CNI 2.0 specification a superset of 1.0 so that plugins that have the 1.0 interface get some sort of default resource type that they expose that's not very flexible, but it's functional, and then you can have a CNI 2.0 provider that gives all of the fancy subtle resources and configurability?
I fully agree with that. I'm talking about CNI 2.0 because the discussion has started a few years ago already, and they are talking, for example, replacing the binary with gRPC model. They are talking about more features, but I fully agree with you, and I think that would be possible to have this just function that provide this capability without having a CNI 2.0. Just, yeah, around the community we have been talking mostly about CNI 2.0, but it's also another example that I have in mind would be the validation. We don't have validation, for example, in Multus of the CNI config. This is something I requested in CNI, and that has to be implemented, but it doesn't really require CNI 2.0, but just an extension of 1.0. But yeah, thanks for the question.
Any other questions? 1 minute left, okay. Okay, here.
Thank you for thank you for the demo. That was super cool. One of the things I was wondering about. So I know that Matcha, talking about the multi-network, and in this example, in your examples, you specifically ask for a named interface, and I'm wondering what you're thinking about for like a level of indirection there, like if the nodes aren't heterogeneous, or rather are heterogeneous, then interface names may change, or even or you may have multiple different types of interfaces attached to the same semantic network, like the internet, right? If you've got an internet But I know that looking at the CNI config embeds that as a master interface name. Like, what are you thinking about for how to create an indirection so that you don't need to specify a specific interface name, but you can kind of, seems like there's multiple places you'd have to have that indirection.
Right. I will try to find this because I had an idea about that, where I can find it. Maybe in this slide. But maybe it's too small. Is it the resource claim template? Or the resource claim and... Yeah. I think here we could reuse the attributes that we have in the resource slice and then put them directly in the CNI config. So we don't have to specify the interface name, but we can have the selector in the select expression and then have the attribute in the resource slice reflected there in the CNI config.
So we would need to be able to capture and modify the config based upon like almost a substitution or template type of thing. Is that what you're thinking?
Right, exactly.
Okay, yeah, we should talk more about that. That's pretty interesting.
Yeah, I was just thinking about that, but I think there's more important things to solve first.
Of course.
And there's a lot of gaps. So, yeah, there was a last question. I don't know if we have time or...
Do we have time or...
Oh, okay.
Hi, I was just wondering, have you thought about just submitting patches to Multus to add a status, fix the annotation so it's not JSON, stuff like that?
There is the annotation right in Multus to have the status where you can report the IP addresses. Just I feel that my problem would be that if I want to deploy on Jiki and I want to deploy on Azure, if they all implement kind of Multus, then the annotation will have different format. I would prefer to have something directly in the Kubernetes API that would provide me the IP addresses, so I can reuse the service or the endpoint slice controller everywhere instead of having an implementation for each of them. But yeah.
Oh, okay, thanks.
Yeah, thanks. So yeah, if there's no other question, thank you for attending and thank you.